Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss surface film and variation of surface tension with temperature. Let's begin. Surface film is a thin topmost layer of liquid at rest, having the thickness which is equal to the molecular range for that of liquid. The molecular range is the maximum distance up to which a liquid molecule can exert some appreciable force of interaction on other molecules. Here usually the molecular range of liquids nearly equal to 10 to the power minus 9 meter. That is for that of surface film. This is about that of surface film. We have to consider a surface film. A surface film. Let we consider a surface film which is being stressed isothermally with the movable bar. That surface film stressed isothermally with that of a movable bar. Here is the liquid, that is the length, and the surface tension of that of liquid. The surface tension of that of liquid be sigma, and area will be A, length A. So here the liquid having that of surface tension will be sigma into L with that amount of force here. Due to that of movable bar that being pulled an infinitesimal distance dx, let that pulled by an infinitesimal distance, here is the distance dx due to that movable bar. So an external force which is only infinitesimally greater than that of sigma L, that is the internal force. So the external force which is slightly greater than, infinitesimally greater than to that of sigma L. This is the force through which it is stressed. Then the small amount of work is done here. The small amount of work is done. Small amount of work is done. Let that is the dW, the small amount of work is done, that is force into distance, that is sigma L dx, sigma L dx. So L dx, that is the area, that is the dA, small area. Since the increase in area, that is why we take the sign convention as positive, that is why the work done is positive. Now applying the first law of thermodynamics, what should be the change in internal energy? Let du. So here we have to apply the first law of thermodynamics. Applying the first law of thermodynamics, let du be the small amount of change in internal energy, small change in that of internal energy. So let we supply dq amount of heat here, that is change to produce the internal energy du plus dw. In place of dw, right here, that is du plus sigma dA. dq here the small change in that of total heat. Now that is we consider here a surface film. That one is the surface film. For that of surface film, surface tension be sigma, area be A. Now the surface tension sigma of that of liquid at constant temperature and pressure also can be expressed in terms of Gibbs free energy. So in terms of Gibbs free energy, let me define the surface tension, sigma of the liquid at constant temperature and pressure, which can also be expressed at Gibbs free energy per unit surface area. Free energy unit surface area, sigma is equal to, that is del G del A at constant temperature, pressure and number of molecules. Sigma in terms of Gibbs free energy, G be the Gibbs free energy. How Gibbs free energy is related to that of particular thermodynamic process? Let all the spontaneous changes of state in thermodynamics are accompanied by that of Gibbs free energy, and that Gibbs free energy is decreases. As the Gibbs free energy decreases, it indicates that the thermodynamic processes are continuous, because the surface of a liquid at rest always is spontaneous and tend to occupy that minimum area. That is why this is possible only when the surface area of that of liquid is not coupled to any other changes in that of energy. Thus, to increase that of surface area, some amount of energy is added. That is why in spontaneous case, del G, here the allowed state, del G is always less than 0. For what? For spontaneous process. Spontaneous process means the Gibbs free energy is always decreases. Now the Gibbs free energy is defined as the maximum amount of energy. Here Gibbs free energy, Gibbs free energy, which is G is equal to H minus Ts means the maximum amount of energy available to a system during a process that can be converted into useful work at constant pressure and constant temperature. That will be G is equal to H minus Ts, where H is the enthalpy, here H is the enthalpy, T be the temperature and S be the entropy. These are the symbols. So, gives free energy G is equal to H minus Ts. Now, if we differentiate that surface tension sigma with respect to the temperature T, what happened? Keeping in mind that dG by dA is equal to, first, therefore dG by dA, that is surface tension is the gives free energy per unit area, that is sigma, the surface tension which is gives free energy, that is the surface tension which is gives free energy per unit area, and that will be what, when you differentiate dG by dA, that is surface tension which is the gives free energy per unit area, that will be S, the G will be H minus Ts, putting the value here in place of G, S0, T as constant, so that will be minus S, that is minus S dG by dA. Now, differentiating the surface tension sigma, differentiating the surface tension sigma with respect to temperature, keeping in mind that surface tension which is gives energy per unit area be minus S. So, we get, that is d sigma by dt at constant area and pressure will be minus S to the power n, n be the number of molecules. That is the expression, that is the surface tension with respect to temperature. All these thermodynamic parameters obtained in case of surface film, that is the surface film, basic idea of surface film. We take an example of surface film, how gives energy and surface tension is related, that is surface tension with temperature. Now, we have to discuss the variation of surface tension with temperature. So, how surface tension varies with temperature. Surface tension of liquids decreases with increase of temperature. When we increase the temperature, the surface tension of that of liquid decreases, means they varies inversely. With the increase of temperature, surface tension decreases, with the decrease of temperature, surface tension increases. And this is because why that happened, due to the larger average separation of the liquid molecules at higher temperature. At higher temperature, liquid molecules are separated largely, means the distance between the liquid molecules are very large as comparison to that of before application of temperature. So, due to the application of higher temperature, the average separation will be maximum. That is why the randomness factor increases, entropy increases, and that leads to the increase in temperature leads to the decrease in its surface tension. Now, here a Hungarian scientist whose name was Laurent Yetvers. Laurent Yetvers. Yetvers. Laurent Yetvers, the scientist, an Hungarian scientist. Proposed the variation of surface tension of an arbitrary liquid at all temperatures, and he studied about how surface tensions of various liquids varies with temperatures, how temperature is related to surface tension for various kinds of liquids. According to his proposal, he made a rule which is known as Yetvers rule. Yetvers rule. According to that rule, Yetvers rule, what is that of Yetvers rule? The density molar mass and critical temperature of the liquids are known. Critical temperature of the liquids are known. At the critical point, according to his rule, in which these factors like the density, molar mass and critical temperature of the liquids are known, then what happen? At critical point, he considered the surface tension to be 0. He considered the surface tension is 0, and the critical point is the end point, and the critical point is the end point of a phase equilibrium. What happened here? Here, where only one phase exists, just remember what that of Yetvers rule to define the variation of surface tension with temperatures, in which the density, molar mass and critical temperature of the liquids are known. Then at critical point, the point is critical point, consider the surface tension is 0, and at that of critical point is the end point of a phase equilibrium where only one phase exists. And he take the assumptions, for Yetvers rule. To find the rule, we take two assumptions. First one, the surface tension of a liquid is a linear function of that of temperature. The surface tension of the liquid is a linear function of the temperature. linear function of the temperature, means he plotted a graph between that of surface tension here. In x axis he take the temperature, y axis he take the surface tension sigma is the temperature T. Plotted graph between that of surface tension and the temperature, and this graph depicts a fairly straight line. So, a fairly straight line, and it also shows that at a temperature called the critical temperature, that is the temperature which is called known as the critical temperature Tc, critical temperature, that is the critical temperature T of C. What happened at that of critical temperature, the surface tension of the liquid drops to 0. Here the surface tension will be 0. That is the first assumption taken by Edwards. Now the second assumptions he proposed to get his rule regarding the relation in between temperature and surface tension. So the variation of surface tension on temperature, the variation of surface tension on temperature can be plotted for all liquids. In a way that we obtain a single master curve for this. What we given for this? The molar mass, the density, or the molar volume are given. Volume of the liquid are known. This is the second assumption by Edwards. The variation of surface tension on temperature can be plotted for all liquids in a way that we obtain the single master curve. For this, what are the necessary factors we have to know? That is the molar mass, the density, and the molar volume is to be known for that of given liquid. That's why we can take a master curve for this. Let V be the molar volume. Let mathematically we can write this. Let V be the molar volume. Tc be the critical temperature of the liquid. That is the critical temperature of the liquid. Critical temperature in the sense the surface tension of the liquid vanishes at a particular temperature which is called the critical temperature for that of given liquid. That is the critical temperature. Then according to Edwards rule, what is his rule? The surface tension of the liquid is directly proportional to the temperature difference. The surface tension of the liquid sigma is directly proportional to the temperature difference to the temperature difference, that is Tc minus T, critical temperature minus temperature, that is the temperature difference. So here we have to mathematical the surface tension of the liquid, let that is sigma V to the power 2 by 3, here V is the molar volume, then the surface tension of that of liquid will be sigma V to the power 2 by 3, which is directly proportional to that of temperature difference, that is Tc minus T, the temperature difference. Now to omit that of proportional, we take a proportionality constant, so let proportionality constant be K, sigma V to the power 2 by 3 is equal to K Tc minus T, K with the proportionality constant. The left hand term sigma V to the power 2 by 3 is known as the molar surface tension, that is denoted by sigma mol, which is equal to K times Tc minus 6K minus T. Look here, what are the new additions to that of particular expression? Here take here sigma mol, that is the molar surface tension, that is the molar surface tension, and we minus 6 Kelvin from that of temperature, where the temperature of 6 Kelvin is always subtracted from that of critical value. Critical temperature for our precise calculations. Now this confirms that the line of the graph was shown in that of figure normally passes the temperature axis 6 Kelvin before the critical temperature. Before the critical temperature it passes the 6 Kelvin. Now adverse rule was first found in 1896, and the correction, which is that is 6 Kelvin, the correction factor was introduced by another scientist, William Ramsay. These are the some basic corrections. This is the correction one, Tc minus 6K, Tc minus 6K is corrected by William Ramsay. And that indicates Tc minus 6K. What is that of indication? Means the line in the graph normally passes, the line in the graph normally passes the temperature axis 6 Kelvin before the critical point. 6 Kelvin before the critical point. Before the critical point, that graph touch it. That indicates particular Tc minus 6K. Read the expression. Sigma mole, that is the molar surface tension, will be K times Tc minus 6K minus T for our calculations purpose. Further, a scientist Van der Waals also proposed the relation between surface tension and temperature of the liquid, According to him, what is that of relation? A relation further proposed by the scientist. According to the scientist, Van der Waals, according to him, the surface tension sigma is equal to k times Tc to the power 1 by 3 Pc to the power 2 by 3 1 minus T divided by Tc. This is the expression for surface tension and temperature according to the scientist Van der Waals. Here k is the universal constant for all liquid. Tc with the critical temperature, Pc with the critical pressure, critical pressure means the pressure at which the surface tension will be 0. That equation was proposed by Van der Waals, relation between surface tension and temperature. Relation between surface tension and temperature by the scientist Van der Waals. So, with the help of this video lecture, we understand what is surface field, how the thermodynamic variables like Gibbs free energy and the surface tensions are related to that of surface field, and the variation of surface tension with temperature, Edwards rule regarding surface tension and temperature, how these two are related, the assumptions taken by Edwards scientist for his rule, and then a mathematical relation proposed by him. Further, a correction is made by another scientist, William Ramsens, for particular temperature. And finally, the relation proposed by the scientist Van der Waals regarding surface tension and temperature. So, with this useful and informative notes, let me wind up this session. Thank you.